Sieve analysis is a standard test used to determine the particle size distribution of aggregate in concrete. For an AI-based platform, accurate sieve analysis is essential to optimize mix design, ensuring improved workability, strength, and sustainability. Well, in this test, I have prepared a representative aggregate commonly used in ready-mix concrete batching plants. This is a fine aggregate or sand, normally range lower than 4 mm. This is a coarse aggregate, range 4 mm up to 12 mm. And this one also is a coarse aggregate, range 12 up to 25 mm. Make sure the aggregates are well dried. Now we have to precisely weigh each samples. Now, using the shaker, we should proceed with the analysis. Now, after completing the shaking phase, we should precisely weigh the remaining on each sieve. This is a sieve analysis for big cross aggregate. As you can see, the majority of proportion belong to sieve number 16 and number 11.2. This is a sieve analysis results for small coarse aggregate. The majority of proportion is belong to sieve number 8. The second rank belong to sieve number 5.6. This is a sieve analysis results for fine aggregate. As you can see, it consists of micro size, 4 mm, 2 mm, and 1 mm.
After performing sieve analysis and recording the mass retained on each sieve, we convert these values into percentage passing to evaluate the aggregate gradation. This is done using the shown formula. The graphs show the gradation curves for 3 types of aggregates: fine coarse aggregate, and large coarse aggregate, based on the percentage passing from the sieve analysis. Each curve illustrates how the particle sizes are distributed across the sieves. The smooth upward trends indicate a well-graded distribution for each type, with the fine aggregate showing a steeper rise due to smaller particles, while the coarse aggregates rise more gradually as larger particles dominate. Our AI-based platform utilizes an advanced classification system that maps aggregate gradation to application-specific requirements using the standardized zone table shown here. By analyzing sieve analysis results and calculating the percentage passing for each sieve size, the platform determines the appropriate zone, Z1A to Z2B, based on the n-value limits. This ensures that the selected aggregate combination meets the structural and workability demands of the concrete application, whether it's for shallow elements, columns, treamy concrete, or high-performance repair mixes. The intelligent classification accounts for placement method, slump target, and material efficiency to recommend the optimal blend of fine and coarse aggregates. The gradation curves visually demonstrate how the AI system matches aggregate distribution with defined zones. By plotting percentage passing versus sieve size, the platform calculates the n-value of the grading curve and compares it to ideal limits for Area 1 and Area 2 applications. This real-time matching allows the system to recommend aggregates that optimize cohesion, segregation control, and compaction based on project-specific requirements.
This graph shows the final gradation curve generated from the experiment we conducted using our AI-based platform. Since the intended application is foundation concrete, which typically requires a coarser gradation for enhanced strength and reduced shrinkage, the platform intelligently selected an optimal blend of aggregates. Based on the input parameters, it determined the mix should include 41% fine aggregate, 33% fine coarse aggregate, and 26% large coarse aggregate.